Traditional robot learning methods require recollecting data from scratch for every new task and environment, which is inefficient and leads to poor generalization. In this work, we propose a method for more effectively leveraging diverse, multitask, multi-domain robotic data to learn new tasks in new domains with better generalization performance. Our approach, which we call pre-training for robots in short, is to first pre-train on diverse multitask data via offline RL, and then fine-tune via offline RL on as little as 10 demonstrations of a target task, leading to much better generalization performance. For prior data, we chose to leverage the bridge dataset by Ebert et al. Since it offers a large and diverse dataset consisting of near-optimal human demonstrations. After pre-training on diverse multitask data, we fine-tune by mixing batches between prior data and target domain data according to an empirically tuned ratio tau. In our work, we show that by using offline RL for both pre-training and fine-tuning, we obtain better generalization performance than imitation learning-based approaches. The key research question in our work is, can PTR leverage diverse prior data to adapt behaviors or learn new user-specified behaviors in target domains? To this end, we evaluated on 3 scenarios. Number 1, retargeting a behavior to interact with a different target object, transferring behaviors to a new target domain, and learning entirely new tasks in new domains not seen in the prior data. Here we leveraged 1,850 trajectories from 31 tasks in a toy kitchen environment to retarget the put sushi in pot task, which uses a transparent orange pot, to instead put the sushi in a metal pot, based on 10 target domain demonstrations. Put sushi in metal pot has never been seen before in the prior data. We find that behavioral cloning on the 10 target domain demos for put sushi in pot in metal pot has a great difficulty executing the task, presumably since BC isn't able to extract sufficiently generalizable representations. By contrast, using PTR to fine-tune on only 10 target domain demonstrations, the policy is able to reliably solve the task. Quantitatively, PTR outperforms by a large margin conservative Q-learning run in zero-shot fashion and BC zero-shot, which both do not use target domain demonstrations, as well as BC fine-tuning, which has access to the same target domain demonstrations. In scenario 2, we test whether PTR can transfer a behavior from the bridge data to a new held-out target domain when provided with only 15 target domain demonstrations. Here, the bridge data consists of 800 demonstrations from 12 different doors in 3 different toy kitchens. We then fine-tune on 15 demonstrations of opening a microwave in a held-out kitchen. Training CQL exclusively on 15 target domain demonstrations yields poor generalization. Fine-tuning with BC also has trouble generalizing to held-out initial robot and effector positions. By contrast, PTR shows significantly better generalization to held-out initial and effector positions. In our quantitative evaluation, all methods are compared across 20 trials, each using the same random initial positions for the end effector for each method. In this task, using the target domain data proves crucial, since not using any target domain data, that is, BC zero-shot and CQL zero-shot, did not yield any successes. We find that jointly training with the target domain data from the beginning yields significantly lower success rates than training on the prior data and then fine-tuning on a mix of target domain data and prior data. We suspect that this is because the network can learn to separately represent the target data, whereas when fine-tuning, it is forced to use the representations learned in the general pre-training phase. Using the target domain data only also achieves low success rates. And finally, PTR yields a success rate of 60% compared to BC fine-tuning at 50%. In the third scenario, we first pre-train on diverse multitask, multi-domain data, and then fine-tune on a number of new tasks in a held-out domain. Note that for all fine-tuning runs, we start from the same general initialization that was obtained in the pre-training phase. For pre-training, we use a subset of the bridge dataset consisting of 80 tasks in 10 different toy kitchen environments consisting of 5,920 trajectories, and we fine-tune on 10 demos each for the different target tasks in a held-out toy kitchen. Fine-tuning BC on 10 demonstrations of the put suite of potato on plate task results in a policy with poor generalization, whereas using PTR results in significantly better generalization to held-out object positions. Similarly, for the put, knife, and pot tasks, we observe that BC is unable to generalize. And by contrast, PTR is able to produce policies that work in a variety of configurations based on only 10 target domain demonstrations. We quantitatively compare PTR with several baselines in the scenario of learning new tasks and new domains for 4 different target domain tasks in a held-out kitchen, where only 10 target domain demonstrations are given for each task. Our method clearly outperforms both BC fine-tuning, joint training with the target domain data from the beginning, as well as training only on the target demonstrations alone. Here we present the architecture we use for the Q function and policy in PTR. In order to make the encoder more sensitive to spatial information, which is crucial for manipulation tasks, we use a modified ResNet with enlarged spatial dimensions of the feature maps at the end of the ResNet stack, as well as a learned spatial embedding, which is pointwise multiplied with the final feature maps and allows the encoder to encode positional information more accurately, as we will show in ablations. Another issue with performing Q-learning on the type of demonstration data we use is that there is a high correlation between states and actions, causing Q functions to ignore actions, since looking at the state is often sufficient to guess the Q value. To prevent the network from relying on this correlation, we encourage it to attend more to action by passing the action vector into every fully connected layer. We will show in ablations that this increases policy performance. Our quantitative experiments show that using the spatial learned embeddings results in significantly higher success rates than using a spatial softmax or global average pooling after the final feature map of the ResNet. We also show in quantitative ablations that passing actions in every fully connected layer of the Q function more than triples success rates, proving it to be one of the most crucial design decisions. We find across scenarios 2 and 3 that increasing model capacity has a large positive impact on performance. This indicates that further scaling the architecture size might bring even larger boosts of performance. The Q functions produced by PTR learn a consistent metric of closeness to the goal, as the monotonically rising Q value plots over time for a successful trajectory on the left and the flat Q values for an unsuccessful trajectories on the right suggest. Because of that, Q value trends can also be used as performance indicators, for example, to select the right models to run experiments with. The Q values for models that do not fit the data well, such as for a model evaluated on a held-out trajectory in zero shot on the left, or for an overfitted model in the middle, do not show clear monotonic trends, whereas a model that correctly fits the data on the right, we see a clear monotonic trend. We conclude that our method, PTR, which performs offline RL pre-training on diverse datasets followed by offline RL fine-tuning on as little as 10 target domain demonstrations, outperforms behavioral cloning. A single model that has been trained on a diverse multi-domain, multi-task dataset can be fine-tuned to perform a variety of different tasks in unseen domains. Similarly to NLP and computer vision, where pre-trained models have become indispensable for initialization, boosting accuracy and generalization, we hope that robotics will similarly benefit from pre-trained models.